Okay, so today we start the convolution of two functions, of course related to the Fourier transform. So before we start the convolution related to Fourier, let me remind you of how we did the convolution when we did the Laplace transform. So let's recall a little about the Laplace transform. So if you remember, in Laplace transform, you have a function that's defined on the interval 0 to infinity to r, of course. And this is the first difference from what we are doing in Fourier transform. In Fourier transform, we have a function that's defined on the whole real line from negative infinity to infinity. In that case, we define the convolution of two functions, something like this. The integral from 0 to x, f of t, g of x minus t dt. We did all the computations. This is not the time for that. But I wanted to remind you of one main property. Why did we do the convolution in Laplace transform? So if we remember the properties, the very simple properties of Laplace, for example, if you take two functions and you compute the Laplace of their sum, that's equal to the sum of their Laplaces. If you take two functions and you subtract them, you get the difference. If you take a function, you multiply it with a number, that number goes out. However, if you look at the Laplace of the product of two functions, can we say it's equal to the Laplace of f times the Laplace of g? Can we say that? The answer is no. This is completely wrong. This is completely wrong. For example, just to explain this to you, Laplace, if you take the function, for example, 1 times x, so basically this is Laplace of x, which is 1 over s squared. But if you claim that the Laplace can be distributed over the product, then this would be Laplace of 1 times Laplace of x, which is 1 over s times 1 over s squared, and it is very clear that the two quantities are not equal. So you can't distribute the Laplace over the product. So this motivated the question for mathematicians. So this was the motivation behind the convolution. So the question is, what is it? Laplace of what is equal to Laplace of f times Laplace of g? Why is this so important? If we go back to differential equations, when we try to solve a differential equation using Laplace transform, in the end, we end up having something like Laplace of something is equal to certain products. For example, it could be 1 over s plus 1 times 1 over s squared plus 1, for example. Then the question becomes very important, because now we want this function here, whose Laplace is a product of two functions. So the question is, what is it here that the Laplace converts into a product of two Laplaces? So this is the question behind the convolution. Then the convolution proved itself to satisfy this property. So if we take this definition for the Laplace, so if we take this, and if we compute the Laplace of the convolution, it turns out to be the product of the two Laplaces. So this is what is so nice about the convolution, and this is the main reason basically we do the convolution. Now, okay, so this is, I wanted to remind you of this stuff before we start the convolution. So please just remember, we did the convolution in Laplace so that we have something whose Laplace is the product of the two Laplaces. I'm going to erase this now. So we start the motivation for Fourier transform. So let's look a little at Fourier transform. So in Fourier transform, you have a function that's defined on the real line. So if f is like this, we define the Fourier transform as 1 over, this is, again, this constant is not a big deal. You can replace it with anything you like. So this is f of x e to the minus I omega x dx. This is called the Laplace transform. Of course, the function has to be integrable. That thing was done before. This is not our goal right now. Okay, so now if we look at the Fourier properties, if you take two functions, let's say f plus g, and you compute the Fourier transform of their sum, what is it? Because we're dealing with an integral, and remember, we did these properties for the cosine and sine transforms. These are the properties on the screen. So similarly, because you are dealing with an integral, if you have two functions, you add them. What is the Fourier transform? Basically, it is the Fourier transform of the first plus the Fourier transform of the second. Same thing goes for the minus. What about if you have a function, you multiply it with a number and you compute the Fourier transform? Again, because you are dealing with an integral, you have a constant, that constant leaves the integral. So basically, you take the constant as is and multiply it with the Fourier transform of the function. However, if you look at f times g and you try to compute the Fourier transform, which is this integral, if you just apply the definition this way, now unfortunately this is not going to be equal to the Fourier transform of the function times the Fourier transform of the other function. There is no way you can distribute the integral over the product, because you have f times g, you can't distribute the integral over the product. So this difficulty, we want to overcome this difficulty by defining a new operation. So usually when we talk about functions, what are the operations on functions? You can add them, subtract them, multiply them with constants. You can multiply them, you can divide them, you can compose them. Remember, these are the basic operations among functions. However, none of these operations allow us to say the Fourier transform of the sum of two functions, or the difference, or and so on. None of them tell us that the Fourier transform becomes a product. That's why we find ourselves in need for a new operation that seems very efficient when we talk about transforms, not only for Laplace transform. The thing we did in Laplace transform basically is a very special case, but also for Fourier transform, for Fourier series, but we did not do it for Fourier series in this course because it's a little bit more complicated than what we have for Fourier transform. The reason for this complication is the fact that Fourier series are defined only for periodic functions. When you see the computations, you will see why. If you're dealing with periodic functions, the computations are a little bit harder. So that's why usually we don't deal with the convolution. However, if we have time, we can talk about it later. Okay, so what's written here is wrong. Okay, so I can't say the transform is distributed over the product. So now we need to define something new, a new operation that's called the convolution between two functions, and this operation must satisfy this needed property. So what is our definition? So if you take two functions from negative infinity to r, and let's say these two functions are L1 functions. Remember, this means the two functions are integrable, and please remember for this course, even if we don't mention this property, we assume it implicitly, because that's the condition for a function to have a Fourier transform. If the function is not L1, it does not have a Fourier transform, so we don't have anything to talk about. Then the convolution, so now we are defining the convolution of f and g is defined by, what is it? So we have a function f star g of the variable x. What is it? It's going to be the integral from negative infinity to infinity. And please, we need to look at this difference between the convolution when we are dealing with Fourier transform and the convolution if you're dealing with Laplace transform. In Laplace transform, the limits were from 0 to x. Now the limits in Fourier are from from negative infinity to infinity. So this is a big difference between the two definitions. However, the integrand is still the same. So what is inside the integral? It is f of t g of x minus t dt. So we need to understand this integral. So in this integral, what happens is t is the variable. X is not a variable. So imagine you fix an x value. For example, you say, I want the convolution at 1, so the x is 1, but the variable of the integral is t. This is very important when it comes to the computations, you will see. Now, this function, this convolution, it turns out that it's always integrable it is always continuous. These are very nice properties. We'll write them later. These are very nice properties of the Fourier transform. But what is most interesting, the most interesting part for the convolution is the fact that then if you compute the Fourier transform of the convolution, it will be f hat of omega, g hat of omega. However, we will have this additional constant. And again, why do we have this constant? This is due to our definition for the Fourier transform. For example, if we define, I'm saying if we define the convolution to be this thing, so if you multiply the integral in the convolution definition by this constant 1 over root 2 pi, then you compute the Fourier transform of the convolution. In that case, you will not see this this constant, and in that case you can say, okay, the convolution converts the Fourier transform into a product. This is so nice. So again, we talked about this constant many times. We can define our integrals the way we like, but with every definition you have some consequences that you need to take care of. In our definition we will have root 2 pi here. Okay, so basically this is the significance of the convolution. Before we start doing examples, let's see basic properties of the convolution. Like, for example, if you compute f star g, and by the way, the way we read this f star g, some people say f convoluted with g, some people say f convolved with g, so it's up to you, convoluted or convolved. So if we compute this convolution, so again this is for any functions, this is this integral, but I want for this property to take this x minus t, and I want to substitute it as y. And remember again, x is not the variable of integration. The variable of integration is t, not x. So what is dt from this substitution? It's negative dy. So if you go back to the integral and you substitute these values, so this becomes the integral of what is t? T is x minus y, g of y. What is dt? It's negative dy. That's fine. Then you say, okay, what about the limits? When t is, because these, the negative infinity, these are the t values. So you need to ask yourself, when t is negative infinity, what is the new value for y? Because y is x minus t, then x minus infinity, you're adding x to infinity, that's infinity, and this will be negative infinity. And now this negative sign here flips the limits of the integral again, so this will be negative infinity to infinity, g of y, f of x minus y dy. If you look at this integral, so now look at this integral and compare it, this one, compare it with this. It's exactly the same, right? The t or the y is irrelevant. Remember, when you deal with definite integrals, whether you write your variable as t or y or anything else, you're getting the same value. So basically, what is this? This is g convolved with f, if you agree. So what is my property? So my conclusion is that f convolved with g is equal to g convolved with f. So this is the first property of the convolution, and this property becomes very handy in certain example. You will see, because the way we look at this integral, when we come to the computations, we will say, okay, take one of the functions and replace x by t if the original variable is x, and the other function replace x by x minus t. So in this replacement, you need to select which function is easier than the other to replace x by t or to replace it by x minus t. And we say choose any function, do whatever you like because of this property, because if you compute f convolved with g or g convolved with f, you're getting the same function. That's why it's irrelevant which function you start with. Then if you like look at other properties like f convolved with g convolved with f, with h, for example, this will be f convolved with g convolved with h. So remember, This property is like the commutative property. This is the associative property. Basically, the commutative in our analysis, the commutative property is more important, and we will need it more than the associative property. The same thing if you have, for example, if you have f plus g convolved with h, and you want to compute this at x, what is this? This is the integral from negative infinity to infinity. For f plus g, you replace x by t. For h, you replace x by x minus t. But luckily, you can distribute. So if we pull this equality back for the space, so this becomes negative infinity to infinity, f of t, h of x minus t, plus g of t, h of x minus t. And I think everybody agrees that this is f convolved with h plus g convolved with h. So this is the distributive property of the convolution. So if you have f plus g convolved with a function, you can basically add the two convolutions. Clearly and similarly, if you have a function f, you multiply it with a constant, and you convolve it with another function g, it's the same as taking the constant out and convolve f with g. It's straightforward. Just write the integral, and because of the constant, you can take it out. And the same if you have the constant with g, you can pull it out similarly. So these are like very basic properties of the convolution. But again, I would say the first property is the most needed for us in this course, and then the more important property and the reason we are learning the convolution is this property. So this property allows you to multiply the two Fourier transforms, and you say, okay, there is a function that's the convolution whose Fourier transform is this product. The other thing, before seeing the example, I like to look at the geometric meaning. So you have two functions. Just imagine your function, for example, imagine f of x was 1 when x is between negative 1 and 1, and 0 otherwise. Just imagine this is your function. So how does this function look like? Between negative 1 and 1, it's 1, then it is 0. And remember, when we draw this function, we like to draw these vertical lines. They are not part of the graph, but we just like to draw them. So this is your function f of x. Now, if this is your function, what about the function? So now let's say this is f of t, because now my variable in the integral will be t. So I'm going to write this as t. So this represents the t, this represents the t. Okay, so now given an x, remember, we look at x in our definition here in the convolution. The x for us is a constant. Okay, we don't look at it as a variable. Okay, so if you look at x, take any x, whether it's positive or negative, it ranges over all the real values. But take any x, and let's draw the function f of x minus t, because this is the other part of the convolution. If you look at the definition again, you have the function replace x or t by x minus t. So what is this? According to our definition, it's 1, but this time if x minus t is between negative 1 and 1, and it is 0 otherwise. If you simplify this just a little, this will be something like this. So if t is between x minus 1 and x plus 1, it will be 0, sorry, it will be 1, and it is 0 otherwise. What does this mean? Okay, what does this mean? This means, just imagine x was 5, for example. If x was 5, this interval here, the x minus 1, x plus 1, this interval, becomes 4 and 6, right? So this is like 4, this is x minus 1, and this is the 6, that's x plus 1 if you look at x as 5. So basically, you have 1 between them and 0 everywhere. So in fact, this is just a shift. If you agree, this is just a shift of the original function. So the original function, this blue curve, is a rectangle over the interval -1, 1. Now you're having the same rectangle shifted 5 units right? That's it, if x was 5. But in fact, it's not a complete shift. It is a reflection, then a shift. Why is it a reflection, then a shift? In general, we're saying in general. In this example, the function is symmetric about the y-axis. So if you reflect it like this about the y-axis, you will be getting the same function. That's why we don't see this reflection. But the idea, when we look at the geometric meaning of the convolution, if you have a function, and then you say, okay, what is f of negative t? This is a reflection through the y-axis. So you have a function, you reflect it as a mirror. Then, what is f of x minus t? This is f of minus t minus x. I'm writing it this way just to go with the basic calculus steps to obtain one function from the other. So from this step to this step, how did we obtain f of x minus t from f of negative t? We replaced t by t minus x. But when you replace t by t minus x, if x, for example, was 5, that means a right shift, right? When you subtract a positive value, it's a right shift. When you subtract a negative value, it's a left shift because it becomes a plus. For example, if x was -1, you will be having f of negative t plus 1, right? But from this step to this step, because you are replacing t by t plus 1, that means you are looking at the left shift by 1 unit. If x was -2, this will be 2 units shift to the left, and so on. So basically, what is f of x minus t in general? F of x minus t in general is this. So imagine, I'm going to draw a different function this time. So imagine you have a function, let's say, like the x cube. Something like this. We don't need to look at the formula, x cube. Then, what is f of x minus t basically? F of x minus t, the first time you flip this, reflect it through the y-axis. So when you reflect it through the y-axis, this is what you get, right? Then you shift it. If x was negative, you shift it to the left. If x was positive, you shift it to the right. But what are the values of x? X can be any real number, so it can be any positive number or any negative number. So basically, imagine x was, for example, x was -1,000. If x was -1,000, that means you need to shift this 1,000 units to the left. If x was -1,000,000, you need to shift it a million units to the left, and so on. So if you say, okay, so as x goes from -infinity, just imagine this, as x goes from -infinity to infinity, what happens? For each value of x, so you take this red curve and you shift it by the value of x. If x was like -1,000,000, that means you are shifting this red curve a million unit to the left. So let's say that's like the infinity, right? Then as x moves to the right, this function moves to the right. And so on. Just imagine we do this for all values of x. Then what happens is you multiply the values for each x. Yes, for each x. You look at this function, the green function, you look at the purple function, and you need to multiply them together and see that value integrated for each value of x. This is somehow how we look at the geometric meaning of the convolution. This integrand, I mean, f of t times f of x minus t. Okay, so now let's see an example, and from that example we will look at the geometric meaning. So let's take, for example, f of x as 1 if x is between -1 and 1, and let's take g of x as and remember, for our purpose in this course, we're dealing with L1 functions, so our functions must be integral, so we can't throw any function like x cubed or x squared in our computations. So let's take g of x as e to the negative absolute value of x, which is basically e to the x if x is negative, and e to the negative x if x is positive. Remember, the equality doesn't change anything. If you like, you can add it here or there. That's irrelevant. It's not our goal. So let's compute f convolved with g, and remember, this is the same as g convolved with f. There is no difference between the two quantities. So f convolved with g is basically the integral from negative infinity to infinity of what? Now, in the integrand, you select any function because f convolved with g is g convolved with f. So you say, okay, let me take f, and in f, replace x by t. In g, replace x by x minus t. Or you can do it the other way. You can say, okay, in g, replace x by t, that's g of t. And in f, do it the other way. You can do it. Both ways are fine. That doesn't change anything. Okay, so basically, again, so this is equal to, from negative infinity to infinity, g of t, f of x minus t. If you do both integrals, you will get the same value exactly. Let's do the other one, okay? Because we wrote it this way. So let's compute the second integral. So this becomes the integral from negative infinity to infinity. G of t. What is g of t? G of t is what's written there, right? It's e to the minus absolute value of t, right? Times f of x minus t dt. Nice. Okay. Now we need to ask, okay, what is f of x minus t? What is f of x? So I'm going to write it here. So what is f of x minus t? F of x is 1 and 0 otherwise, and it's 1 when x minus t is between negative 1 and 1, right? So basically, if you multiply this by negative, this is what you're getting. Negative x plus t equals. So the t is between x minus 1 and x plus 1. So I'm going to write it this way. So the t is between x minus 1 and x plus 1. So why is this so important? Why is this so important? The t values, if you go back to the integral, the t values are from negative infinity to infinity. So they are running over all real numbers. But many of those values are zeros because, for example, if x was 1, you are saying that when t is between 0 and 2, you have values for the function f. But outside that interval, the values are zeros. So basically, you don't need to take all real values. So this integral, in fact, becomes the integral not from negative infinity to infinity. Instead, it becomes from x minus 1 to x plus 1, e to the minus absolute value of t. And what is f of x minus t there? It's just 1. That's the value of the function in that interval. So this is the type of integrals we have in this example with the convolution. And this we will see. I'm not going to say these computations are difficult, but we need to be very careful with these computations. Okay, so now we have this. So if you look at the real line, this is 0, and I'm sure you know why I started by writing 0, because we're dealing with e to the minus absolute value of t. The absolute value depends on whether the quantity inside the absolute value, which is t, is positive or negative. Now, what are the t values? The t values are between x minus 1 and x plus 1. But we don't know what x is. X can be any real number. For example, imagine x was 2. Then what are the limits of the integral in this example? The limits are 2 minus 1, which is 1, 2 plus 1, which is 3. So in this case, the limits become 1 to 3, which means the t values are positive. So you don't need to have the absolute value there. However, if x was, for example, negative 1, in that case, if x was negative 1, you will have negative 2 up to 0. This is the t. In this case, the t values are negative, so you need to say the absolute value of t is negative t. That's very, very crucial. But also sometimes, like, for example, let's delete these numbers. Like, for example, just imagine the x was 0. Then if x was 0, what are the limits of the integral? They are from -1 to 1, and the t values are between them. So sometimes the t is negative, sometimes the t is positive, which means you need to split the integral. So now we need to decide. When to split the integral. Now I think we all agree that when x is bigger than or equal to 1, what is the lower limit? The lower limit is x minus 1, right? Which will be, if you move the 1, will be positive. So if x, so I'm going to write it this way, okay? So now I'm deleting these things just to avoid any scratches. Okay, so I think we all agree that if x was bigger than or equal to 1, in that case, what are the limits? The limits are x minus 1 to x plus 1, but in that case, the least limit is going to be 0, and the x plus 1 will be somewhere positive. So in that case, the t will be positive, and in that case, the integral becomes the integral from x minus 1 to x plus 1 e to the minus t dt. So you can remove the absolute value without worrying about anything. On the other hand, if x was smaller than or equal to -1, so what happens in that case? So you are talking about the left part. So in that case, what is the upper limit of the integral? The lower limit is x minus 1 again, the upper limit is x plus 1. But if x is less than or equal to -1, if x is less than or equal to -1, when you move the -1, this gives you that x plus 1 is always less than or equal to 0. So that means if x is less than or equal to -1, your t will be to the left. If your t will be to the left, then what are the limits of the integral? They will be e to the positive t dt, because in that case the absolute value of t is -t. However, it seems that when x is between the two values, x between -1 and 1, what happens in that case? In this case, if you write it, x is between -1 and 1. So if you write it as two inequalities, so if you write -1 less than x and x less than 1, in this case you're saying that x plus 1 is bigger than 0, x minus 1 is less than 0. So in this case, what happens is exactly this. So if we erase this line and you draw a new line, so in this case what you're saying is x minus 1 is to the left and x plus 1 is to the right. So when you do the integral, you have two sets of t values. Some of them are negative to the left of 0, some of them are positive. So in this case, we need to split our integral. How do we split our integral? We will split it as from x minus 1 up to 0. In that case, the t values are negative. This becomes e to the t. And from 0 to x plus 1, e to the -t dt. Sorry, this has to be So this is 1. This is -1 less than x less than 1. Of course, the equalities do not change anything. If you like, you add the equalities here or there. The convolution is always continuous. We'll write this later. Okay. So let's compute this integral. What is this integral? But usually we prefer to start with the smaller values. So when x is less than or equal to 1, what is this integral? The last integral. So it's e to the t. It's the same thing. From x plus 1. Up to x plus 1. So if you integrate e to the t, it's e to the t. You substitute the upper limit, x plus 1, minus you substitute the lower limit, x minus 1. Then what happens when x is between -1 and 1? You go to the intermediate integral from x minus 1 to 0. So the integral is e to the t. If you substitute the 0, it's 1 minus e to the x minus 1. Then plus, what about e to the minus t? The e to the minus t gives you a minus sign. This is it. You substitute the x plus 1, so that's e to the minus 1 minus x, minus you substitute the 0, that gives you -1. And when x is bigger than or equal to 1, e to the negative, so you have a negative sign. You substitute the x plus 1, it's going to be e to the minus 1 minus x, minus you substitute the lower, it will be 1 minus x. So if we just rewrite this as e to the x plus 1 minus e to the x minus 1 when x is less than or equal to negative 1. If you collect the terms in the middle term, you will have 2 minus e to the x minus 1 minus e to the minus 1 minus x when minus 1 is between x, when x is between negative 1 and 1. And the last one will be e to the 1 minus x minus e to the minus 1 minus x when x is bigger than or equal to 1. So this is the convolution. This is the convolution. So you see we have some computations of these two functions, the rectangle with the exponential. Now, if you look at the original functions, the exponential function is a continuous function because it's e to the absolute value. But if you look at the rectangular function, 1 between negative 1 and 1 and 0 otherwise, this function is not continuous. It has jumps at negative 1 and 1. So in this example, I'm just going to show you this in this example. So the original function f looks like this. It's a rectangle. So it is not continuous, okay? It's not continuous at these points. However, if you look at the convolution of the two functions, now each of these functions appearing in the convolution, each rule, this one alone, this one, each of them is continuous. But the question is the function composed of the three functions continuous? That means we need to look at the endpoints. We need to look at negative 1 and 1. Now, nicely, if you substitute the negative 1 into this function or into this function, you will get exactly the same value. Try it. If you substitute the negative 1 into the first formula, what do you get? You get e to the 0 minus e to the negative 2, right? If you substitute it into the second one, you'll get 2 minus e to the minus 2 minus 1, which is exactly 1 minus e to the negative 2, which is exactly 1 minus e to the negative 2. So if you substitute the negative 1, the two formulas give you the same value. That means the function, the new function, the convolution is continuous at negative 1, although the original function was not continuous. F was not continuous at x equals negative 1. This is a nice property that we will write in a minute. So this is one way, by the way. This is one way we check our answers, because in the convolution, as you've seen already, we have some computations. So there is a chance for doing some mistakes. So one way to check our answer, when you finish your computations, just look at your function, the result of the convolution, and ask yourself, is this function continuous? If it's continuous, that gives you a clue somehow. Your solution would be fine. It doesn't mean that's completely true, but this is an indication that you are fine. You are fine, okay? Okay, so this is the convolution of the two functions. I'm going now to write the remark that f convolved with g is always continuous regardless of f and g. I mean regardless of the continuity behavior of f and g. F and g, the original functions, could be discontinuous, but their convolution is necessarily, it has to be continuous. Of course, this is a theorem that has its proof in Fourier analysis, which is, I think, more advanced than the level of this course, especially for engineering students. But if you search it, Google it, you'll find many proofs, I think. Okay, so this is the computations. These are the computations of the convolution. Now, in this example, I like to show you graphically what happens. So if we draw stuff like this, for these particular functions f and g, what happens exactly, and how can we look at the computations in terms of the graphs. Okay, so what I'm going to do is, if you look at this function, if you look at what we did, in fact, if we look at what we did at this step exactly. So for the function, the exponential function, we just replaced x by t. So basically, this function did not change, okay? So I'm going to draw the exponential function first. So the exponential function is like this. So this part here is e to the negative t. This part here is e to the t. Okay, this is the exponential function. Then what about the function f of x minus t? Okay, because we in our computations, in our analysis, we had the function f of x minus t. Now, how do you draw this function? Again, you go back to the function f. What was the function f? The function f is the rectangle. Okay, it's 1 between negative 1 and 1. So basically what you do is this. You draw negative 1 and 1 between negative 1 and 1 like this. This is your function. You reflect it about the y-axis, but you still have the same thing. Then you shift it from infinity. So you shift it back and draw it this way, okay? And then you start moving it to the right. So as x moves to the right, this graph moves to the right. So basically, what do you have for the function f of x minus t? You will have, as we've seen above, x plus 1 here, x minus 1 here. You have a function like this, and which is 0, 0 everywhere. And just imagine this function is moving, okay? So as x moves to the right, this rectangle that we have in red, it's moving to the right. So at a certain moment it will be here, then it will be somewhere here, like this. Just imagine we do it, then it will be something like this here, and so on. So just imagine this. Then ask yourself, if you multiply the two graphs that you're seeing on the screen, so if you multiply the red curve with the blue curve, in this particular case, in this graph that you are seeing right now, everything outside like this, everything here will be 0 because the red thing is 0. So if you multiply it with the blue curve, you will be getting 0. So basically, that's why you'll be getting the integral from x minus 1 up to x plus 1 only. For what? For the blue curve, which is e to the t, times the red curve, which is 1 in that interval, right? That's true as long as your rectangle is completely to the left, right? So for example, if your rectangle is like this, you'll be getting the same thing. But the problem is when your rectangle crosses the y-axis, then you have to think differently, okay? So that means as long as x plus 1 is to the left, which means x is less than or equal to negative 1, you will have exactly this integral. If you go back to our computations, when x is less than or equal to negative 1, this is what you have, right? Which is exactly this. So you can interpret, you can understand things geometrically and do them aside, then do your math, or you can analyze them as we've done here mathematically. But this is the graph behind these computations. Okay, so this is the first thing. After that, you say, okay, so when this rectangle crosses the y-axis, that means x plus 1 is to the right and x minus 1 is to the left. But this happens when x is between negative 1 and 1. So you want like this. You want x plus 1 to be bigger than 0 and x minus 1 to be less than 0, right? That means x is bigger than negative 1. At the same time, x is less than 1. So this is negative 1, 1, and x is between them. This is exactly how we obtained this interval in our computations. This is exactly how we obtained this interval. And in that case, what is my integral? So I need to multiply now. Let me erase the other stuff so you're not confused with anything. So I'm not having this anymore. I'm not having this. I'm just having this green rectangle that crosses the y-axis, okay, like this. So now I want to multiply the green curve with the blue curve. But again, after the x plus 1, if you look at the interval, here the green curve is 0, here the green curve is 0. So basically you're just integrating over x minus 1 up to x plus 1. But in this case, the blue curve, if you look at the blue curve, you have two formulas, right? On the left, you have e to the t. On the right, you have e to the negative t. So that's why you need to split your integral exactly at 0. So that's why you have to do it from x minus 1 to 0, then from 0 to x plus 1. Between x minus 1 and 0, the blue curve is e to the t, but the green curve is 1. On the other side, it's e to the negative t times 1, and that's exactly what we have here in our analysis for the interval from negative 1 to 1. So again, we did that without doing any graphs, but now this is the graph behind our computations, and similarly you can analyze what happens when x is bigger than 1. So this is our first example on convolution of two functions. Again, there is some geometry, but to find the final answer for the convolution, you have to do the integral. So the geometry can simplify for you the limits of the integral, the way we understand it and analyze it. But for the computations, you have to do an integral. So this is one example. We will be solving other examples on convolution in next